Okay, as you may remember way back before the exam, we'd started looking at how things really happened, how people were able to figure out about bonds and how atoms were arranged and molecules reacted before there were the powerful techniques that developed mostly in the last 25 or 30 years as far as their practical application in organic chemistry. But how they found these out before that time. And it started with what we call the chemical revolution, which was launched by Lavoisier with this book in 1789, the same year as the French Revolution, the Elementary Treatise of Chemistry, which you remember he started work on just because he was interested in improving nomenclature, but found that there was such a tight coupling between nomenclature and the science, that is the facts and the theory, that he couldn't improve any one of them without improving the others. So we saw last time that he developed, that in the process of developing a new nomenclature, he also developed instruments so that he could weigh gases, because weighing turns out to be such an important feature in all of 19th century chemistry, no doubt the most important single technique. But he also could measure heat, which didn't have any weight. For that, he developed a calorimeter together with Laplace, and we saw how that worked by melting ice. So now we're going to look at some of the other developments from this book. In particular, the idea of oxidation. There's no doubt that the most important element for Lavoisier was oxygen because of its key role in his chemistry, so that all other elements were called bases or radicals, right? And they could react with oxygen to become new things. There were several degrees of oxidation, as shown in this table from the English translation of his book. So first you'd get an oxide, oxides of all the elements that are listed in the first table. For example, hydrogen, when oxidized, would give water. That's the second row. But the first row is caloric. This was sort of a stretch, at least it seems so from our perspective, that caloric heat, when it gets oxidized, yields oxygen gas. But then there were further degrees of oxidation if you reacted with more oxygen. So their second degree of oxidation, according to his theory, was to give an acid that the suffix was to be systematically OUS, so us. And those names we use now, like cuprous, ferrous, come directly from this work of Lavoisier. So that's the lower oxidation state of an acid, right? So you have, for example, nitrous acid, carbonous acid, sulfurous acid, phosphorus acid, he said. And then you have a still higher degree of oxidation, the third degree, which is the ic acid. So you have nitric acid, carbonic acid, sulfuric acid. And notice that many of these were not known, and many of them still are not known because the theory wasn't exactly right. For example, carbonous acid was not known at that time. You see in the second entry in the second row, second column. Okay, and then there was still a fourth degree of oxidation, which he called the oxygenated ic acid. He didn't use the peroxy acid as we would often use nowadays, but he used, for example, oxygenated nitric acid, which was unknown. Oxygenated carbonic acid was unknown, same for sulfuric or phosphoric. And oxygenated muriatic acid was used to be called dephlogisticated marine acid, but he has a more systematic name showing its degree of oxidation. So these us and ic names that we still use come directly from Lavoisier. And probably the next most important tool he developed was one for doing elemental analysis. Remember, you could do proximate analysis, what other compounds are present in the substance you're studying, or you could do ultimate analysis and find out how much of the elements there was in each. And this was how to do elemental analysis of an organic oil. So it has carbon, hydrogen, oxygen in it. Okay? So this big upside down barrel inside another barrel with water in it is how he got air for the burning, because the upside down barrel would be lowered into the water, which would create pressure in the oxygen that's trapped inside. It would then flow out through the pipe you see coming from the tank, through a dryer, and into this big vertical cylinder where the combustion takes place, fed by an oil supply, which is siphoned in as needed. So there's a lamp inside burning the oil with the air, and the vapors generated by the combustion come up and out the tube to the right. So there's the lamp. The gases come out, and water gets condensed in the spiral tube in here and drips down and gets collected in the jar that you see. And the part that doesn't condense and get collected in the jar gets absorbed in that horizontal tube that has calcium chloride drying agent in it. So at the end of the experiment, you weigh how much water there is in the jar and how much the calcium chloride has increased in weight, and that tells you how much water there was. And what does that tell you about the compound? How much what? What element is being measured in the oil by weighing the water? It's measuring the hydrogen. So he had to know what percent by weight water is of hydrogen. Then if he measured the water that came from combustion, he measured how much hydrogen there was in the oil sample that was being burned. And then the gases continued to go through lime water, calcium hydroxide. So that would absorb CO2 as calcium carbonate. So those would increase in mass, and he had 2 of them, so whatever got through the first one would hopefully be collected in the next one. And then there's another drying tube on further from that, because these solutions, as you pass gas over them, they lose a little bit of their water, right? So they'd be losing weight as well as gaining weight from the CO2 that's being absorbed, right? But that water that's lost is reabsorbed in that final tube. So you weigh it at the end, and now you've corrected for whatever loss of water there was from the bulbs. And now you know what weight of CO2, and if you know what fraction of CO2 is carbon, and there's a homework problem for Friday that you can look at. You can work in groups on that. That shows you how he knew how much, what weight percentage of CO2 was carbon. So having then measured how much CO2, he knew how much carbon there was in the oil. So he measured the hydrogen, he measured the carbon. So that's fine if it's a hydrocarbon oil. How about if there was oxygen in the oil? Notice he's adding all kinds of oxygen from the air. So how's he going to know how much oxygen there was if it was an alcohol or something that he was burning? Sam? Can't hear you. It's the leftovers. You see how much oil got burned, how much carbon, how much hydrogen, and you assume there's nothing else there except oxygen. So you get oxygen by difference. And that's the way oxygen is almost always measured, is by difference, right? So you assume, and you have to be sure there are no other elements there if you want that to be true, obviously. Okay, so this was a big operation, and it took, somebody to control the air supply to make sure it was constant. Notice, incidentally, there's a T here. So there was another one of these things over here, another one of these double barrels, right? Why? So when you run out of air in one, you switch the valve and take it from the other one, then you can go back to the first one, so you have an infinite supply of air, plenty to burn the oil, right? But you need someone to control that, and you need someone else to make sure the lamp stays lit, that it gets the proper amount of oil siphoned in and the airflow is right. You need someone else. In the CO2 collectors, you just blow gas over the surface, right? So it's got a little key on the top and a hook that goes down in, so somebody has to be standing there doing this to keep it stirred, right? So it takes at least 3 or 4 people to run this thing, right? And it cost a lot of money to build, so no one else built one. In fact, it's not absolutely certain that Lavoisier ever used this, although it exists, right? Because he was busy with other things having to do with the French Revolution by the time this came along. But this was big science, right? He was very wealthy, so he was able to do this kind of thing. But he showed in this diagram exactly how it could be done, so it was no secret, not like what the alchemists did. Was there a question here? No. Yeah, Lucas? Did they measure
the amount of air that they gave into it?
I don't think so, because there wasn't any purpose. You didn't care how much air you put in. Because most of the air just flowed right on through. It was never collected, right? It just carried the other gases along where the water and the CO2 would be collected.
Like, I guess if they knew the content of the air, like they could just measure how much oxygen.
To get the oxygen? Conceivably, but that was never done. It would have been very difficult to collect all that air and measure it accurately. Okay, now, what if you have a substance that won't burn cleanly, so you can't measure these gases? Notice, incidentally, the role of gases in understanding things, because they provide easy separation, right? And then, since he was able to weigh gas once, then he knows the gas density. So now all you have to do from then on, in principle, is measure the volume of gas, and you know how much stuff there was. So gases played a really key role through all this. But suppose you had a substance that wouldn't burn, that you couldn't convert to steam and CO2. What do you do then? For example, grape sugar. So here's chapter 13, where he talks about le sucre de raisin, the grape sugar, which will char. It won't burn cleanly. So what do? Well, as he says up at the top there, tout le monde fait comment se fait le vin. Everyone knows how to make wine, cider, and mead, right? So can you see what he's going to do? So here's the device for that one, which is in many ways sort of similar, but you don't need an air, you don't put the air in. What you have is a big flask at the beginning, which has sugar, yeast, and water, right? So the yeast ferments the sugar and changes it into CO2. So you have, it foams up, if you've ever seen something fermenting, so you have to have something that catches the foam so it won't get into your device. And then you have something that will absorb water. Now the water is not just, it's not like the previous one where the water is all formed by the thing, because you've got a whole bunch of water there at the beginning, right? So that's not what you're trying to measure. What you're trying to measure is how much carbon, how much CO2 there is in the grape sugar. So you have these sodium hydroxide solutions, the base that will absorb the CO2 as carbonate, so you weigh those before and after. And the excess gas, if there's another gas being evolved, will collect over the mercury in the far tube here. So we could measure the carbon in sugar by converting it completely to CO2 through fermentation. In speaking of fermentation here, he says it furnishes a means of analyzing sugar. So oxidation failed with air, even with oxygen or sulfuric acid or mercuric oxide. You couldn't get clean combustion of sugar. You got charring instead. But as he says here, this is the most interesting thing about his treatment of the data. He said, I could consider the materials subjected to fermentation and the products of fermentation as an algebraic equation having to do with weights. And can you see what his assumption is going to be here? Sam? The same weights on both sides. Conservation of mass is his assumption. Okay? So he can make an equation that the weight on the right and the weight on the left will be the same. Okay, so an algebraic equation. And by in turn, supposing each of the elements of the equation to be unknown, I can derive a value and thus correct experiment by calculation and calculation by experiment. So what does he mean by that? So if you have this equation, a certain amount of sugar and a certain amount of oxygen gives a certain amount of CO2, for example, right? So the weights on the two sides should be the same. He doesn't know one of them, right? But if he knows all the others and it's an algebraic equation, he can then solve for that one. So he says here, I can derive a value and thus correct experiment by calculation. Have you ever heard of that being done? Lexi? Would you do that in lab? Correct experiment? Do you suppose there might be any nefarious people who would correct their experiments by calculation after finishing a lab? No, I can't imagine that would happen, right? Okay, but Lavoisier was up front, right? He was even, one might say, bragging about it, that he has this algebraic equation so he can correct his experiments, right? I've often profited from this way of correcting the preliminary results of my experiments. No one told him that that's not the way science works, right? That the experiments are the things you have to adjust the theory to deal with the experiments. Okay? So he was, remember, he was the treasurer for the firm that collected taxes for the French crown, right? So he was accustomed to bookkeeping, and everything had to balance right down to the sou, right? So the same thing he applied to chemistry. So table 1 here is the materials of fermentation. He put in a certain amount of water, 400 pounds, a certain amount of sugar, 100 pounds, yeast. Now he knew that the yeast was wet, so there was a certain amount of water. He took 10 pounds of yeast, but he knew by analysis, by proximate analysis, right? Not how much, not what the elements are, but what the substances are there. That in 10 pounds of yeast, wet yeast, you'd have 7 pounds, 3 ounces, 6 grow, and 44 grains. It turns out that a grow is a 72nd of a grain, and 8 grow make an ounce. So it's a grow which is 28.35 grams. So if you want, you can work through all this. Do you think he had analyzed things that accurately? That he knew right down to the grow how much there was in there? No, he couldn't. There's no way he could have known that. But things had to balance, right? So he made an approximate thing, and then he carried it out to 18 decimal points the way you'd do on a calculator, right? Okay, so he didn't know about significant figures yet either. Okay, so then in table 2, he figures in that much water, sugar, yeast, how much is there of, in each one, how much is in water, how much is hydrogen, and how much is oxygen. So he knows that. So now he knows down to hundredths of grow how much of each of those elements there are in the 400 pounds of water he's using. Incidentally, he never used 400 pounds of water. He just rounded his numbers up, or multiplied his numbers, scaled them up to be that big. He used large quantities, but not that large. Okay. So if you had 100 pounds of sugar, you'd have a certain amount of hydrogen, oxygen, and charcoal, that is carbon. And if you had a certain amount of the dry yeast, you'd have that. And then he makes still a third table where he rearranges it, so he pulls the elements all together. So in the starting material, how much hydrogen, oxygen, carbon? Okay, so he's got 411 pounds, 12 ounces, 6 grow, 1.36 grains of oxygen, grains and grow, got it. Oh, grow and grains, okay, right. Okay, that much oxygen, and some amount of hydrogen and charcoal, and a certain amount of nitrogen that's in the yeast, because that's enough, he knew that was there. Okay, which is just a small weight altogether because there's not much yeast. And in all, 510 pounds exactly, right? So his balance sheet was just like what a banker would want. Okay, and now he looks at the products, and he has a certain amount of CO2 that he collected, that's carbonic acid, and he knows how much oxygen and charcoal there is that. A certain amount of water, a certain amount of alcohol, if dry, so he had to collect the alcohol and say how much alcohol and how much water was in it, how much acetic acid, how much residual sugar that hadn't fermented, and how much dry yeast there was at the end, and he added them all together, and by God, there was 510 pounds, 0 ounces, 0 grow, and 0 grains, right? QED. Okay? And then he recapitulated it according to how much oxygen, how much charcoal, and how much hydrogen. And that, once again, it balances out absolutely precisely. Okay, so he recapitulates it that way. And this is how he would do some of these things. Okay? So this is a description of an experiment on page 88 to 92 of the Traité élémentaire. Okay, so he's got a fire burning here and a glass tube that runs through the middle of the charcoal that's burning. Right? And he's got a flask cemented to it on the right, which is over a burner. And in the tube, he puts 28 grains of carbon. That, not pieces, but a weight of 22 grains. We saw what a grain was last time. That turns out to be 1.38 grams of carbon he's got inside the tube. Okay, and now, do you think the carbon will evaporate, incidentally, if you put it in flame? You know how? How do you know it won't evaporate? Where do you get carbon? What did he call it?
Charcoal.
He called it charcoal. You get charcoal in a flame, right? So with burning without enough oxygen. So obviously it's not going to evaporate, it's just going to sit there. Okay, so in flask A there, he puts water. So there's water in it. And then he lights the fire underneath, and the water begins to boil and distills through the tube and collects over here in H. Right? There it comes. Okay? But did you notice what happened in the process? Let me back up and do it again. What happened? The charcoal went away. What happened? Well, let's see what he found. So, the 28 grains of carbon was gone, right? And in the end, he got the water that he put in at the start, but not all the water. It was 85.7 grains short. So all the carbon and some of the water is gone. Where did it go? Well, it went out the tube. So out the tube, he said, came 144 cubic inches, and because he knows the density, he knows how much weight that is, 100 grains exactly of carbonic gas, CO2. We would call it CO2, and 380 cubic inches of flammable gas. So one of them would be collected by lime water, the carbonic gas, and the other one would go right on through. What do you suppose flammable gas is? Hydrogen. So the oxygen went to the carbon, and the hydrogen became elemental hydrogen in this process. Okay? Now, look at this. This is what's neat. So we got 100 grains, of carbonic gas and 13.7 grains of hydrogen, the stuff that gives water when you burn it, according to him, right? Which is right, which is correct. And what do you notice? Quantitatively, they exactly match, right down to the tenths of grains. Okay. Now, if you recalculate by modern theory how much gas you should get from 28 grains of carbon doing this, you should get 157 cubic inches and 313 cubic inches instead of 144 and 380. You should get 103 grains of carbonic gas and 9.4 grains of flammable gas. So his experiments weren't perfect, right? Which is not surprising, and there's no shame in that. But what would we now say he did wrong? He adjusted his results to fit his theory. Okay? But this was early days. He actually said on page 92, I have thought it best to correct by calculation and to present the experiment in all its simplicity. Now, what's wrong with presenting an experiment in all its simplicity? You lose anything that's new, anything that you might have discovered in the experiment. Okay? But he was discovering a lot of stuff, so we'll forgive him that. Okay? He was certainly a great scientist. So what were his contributions? Clarity above all, right? This idea of facts and ideas and words having to go together and improve together. And of the facts he worked on, there were the apparatus I showed and others as well. Important thing was quantitation, using numbers, which people hadn't used before, not nearly as effectively at least. Concentrating on making things balance. Using mass as the criterion for how much stuff you have, but also, in the case of gases, volume, but measuring the density so that you can relate volume to mass, which is the fundamental quantity. He found some new substances, although that wasn't much of a contribution on his part. Other people like Scheele before him had discovered lots and lots of new pure substances. That wasn't Lavoisier's strong suit. And reactions. And then with respect to ideas, the idea of what an element is, that it's not some Platonic ideal, but it only means as far as we've so far been able to go in analyzing things and breaking them down. And if we can't break them down further, we'll assume for the time being that they are elements, but it may be that they won't be in the long run. The idea of conservation of mass, of course, is key. Oxidation as the organizing principle. The idea of a radical, that an element is the base of something and that it can become an acid through oxidation. And the idea of salts from mixing of elements. And with respect to words, the idea that names should be meaningful. In particular, the names for elements, oxidation states, so he developed these suffixes, us, ik, ide, ite, and ate are all due to Lavoisier. And the idea of the salt composition, the way of naming them, that sodium hydroxide, for example, or sodium chloride, or chlorate, or chlorite, which are different degrees of oxidation of the element. Okay, but like everyone who would follow and everyone before and everyone nowadays, he was plagued by lack of imagination, right? That's always the short suit of everyone who's in science or probably in anything. He said, at the end of this preface that we've talked about, chemistry's present progress, however, is so rapid, and the facts under modern doctrine have assumed so happy an arrangement that we have ground to hope, even in our own times, to see it approach near to the highest state of perfection of which it is susceptible. Right? So people always think that there are a few things that you can see you have to do to fill in little chinks here and there, but otherwise, we've got it now. Right? This is certainly what a lot of people tended to think about the human genome. Once you know what the human genome is, then all diseases are solved, everything else, right? It's never been true, and it almost certainly is not true now. And it certainly wasn't true in his time. He said, even in our own times. He wrote this in 1789. And in 1794, he was guillotined. So he certainly didn't happen in his own time. The judge, Coffenhal, is reported to have said, although perhaps apocryphally, that the Republic has no need of geniuses. And in fact, all his equipment was seized for the people, including his 80 pounds of mercury that he carried around in this thing to measure gases. That madness lasted only a couple years, maybe not even that long. And his widow recovered the equipment, and it currently is in the Musée des Arts et Métiers in Paris. I've never seen it, but a number of students from the class have sent me postcards when they've gone to see it. Okay, and Lagrange, the guy that helped him build the calorimeter, wrote, "It took them only an instant to make this head fall, but 100 years may not suffice to reproduce one like it." So what we're going to look at is what the heads in the next 100 years were able to accomplish. So today we're going to do the first 20 or 25 or 30 years after Lavoisier to see where things went. So we've looked at Boyle and his gas laws and Lavoisier, and now we're going to go on to Dalton. So here's John Dalton, who lived up near the Lake District in England, and he was an amateur meteorologist. So he was interested in keeping weather records and so on. And in particular, he was interested in why in the atmosphere, if you collect air at the top of a mountain and down in the bottom of a valley, you get the same composition. Why don't the heavier gases sink and the lighter ones rise? Good question, right? Well, people on the continent had proposed that different gases attract one another, so they tend to stick and therefore stay mixed. Right? But Dalton had a different idea, and this is a picture he drew of gases. The top is azote, or nitrogen, and the bottom is hydrogen. So he said the atoms of one kind did not repel the atoms of another kind. It's not, well, you'll see just a second. Okay, so the center is his symbol for the atom, nitrogen in that case, and surrounding it, this sort of halo, is the envelope that's heat associated with that particular atom. So these rays come out, and if the rays meet one another between adjacent atoms in the gas, then they repel one another, according to Dalton's theory. But if they don't match, as in hydrogen and nitrogen, then they don't repel one another. Right? So atoms of the same element tend to stay apart, but the atoms of the other element are completely free to be inside there. They knew that the pressure went down as you went up, that was no question, right? But why don't they stratify? It's because the different elements don't repel one another. So he substituted homo-repulsion, that the same atoms repel one another, for what the Europeans used as hetero-attraction. Okay? Obviously that turned out to be nonsense. But Dalton developed three principles in terms of these atoms that he had started using for this purpose of something about the atmosphere. These principles have come to be known as definite proportions, equivalent proportions, and multiple proportions. So definite proportions is that pure compounds always have the same weight ratio of their elements. So you don't get a sample of sugar here that's a certain percentage of carbon and hydrogen and a slightly different percentage of carbon and hydrogen here. And he explains it by saying that these compounds are a given ratio of elements. So you have that same ratio all the time when you have a particular compound. Now, equivalent proportions is a pretty simple idea, but it looks complex. Okay, so suppose you have a certain weight of A reacts with a certain weight of B, okay, to form AB, okay? And a certain amount of A react with a certain amount of C to form AC. But if it's the same amount of A, then in some sense, that weight of B and that weight of C are equivalent to one another, okay? Because they react with the same weight of A. So they're equivalent. But now suppose you have another compound D that also reacts with B parts of B. A reacted with B parts of B, right? What does that tell you about equivalence? That means that A parts of A is equivalent to D parts of D, okay? So just for, suppose 2 grams of A reacted with 3 grams of B, and 2 grams of A reacted with 8 grams of C. That means 3 grams of B is equal to 8 grams of C for purposes of combining, okay? And suppose 1.5 grams of D also reacted with 3 grams of B. Then 1.5 grams of D is equal to 1 gram of A, okay? Now, what could you conclude? What's the final line going to be? What do you predict from this if you have these kinds of equivalents? An equivalence between B and C and an equivalence between A and D. You see? Then you predict that if you react D and C, what's going to happen? What rate ratio will they be in? Okay, D parts of D will react with C parts of C, right? Because the D is like the A in the beginning, the C is like the B in the beginning, so D parts of D should react with C parts of C. That's what multiple proportions is. I'll show you an example, okay? And finally, multiple proportions. If the same two elements form several different compounds, the weight ratios are related by simple factors, and I'll show you an example of that. So these are all things that Dalton adduced as support for the idea that things were made of atoms, fundamental units. Now, definite proportions. Does the same compound always have the same ratio of the elements in it? The French school was divided on this question. Berthollet said no, and Proust said, because he said they're metal alloys or natural organic materials that vary in their analysis, right? Okay, and Proust said, oui, right? And that defined what chemistry was. That chemists then began to deal only with things that obeyed this law of multiple proportions. They didn't deal in fundamental ways with alloys or with complicated big molecules that had really complicated formulas or couldn't be separated as mixtures and therefore got different analyses at different times. They assumed that anything that was pure had this, obeyed the law of definite proportions. So it was really more of a definition, right, than a law. Okay, now multiple proportions. So there were oxides of carbon. You remember Lavoisier, 1789, found 44% carbon, 56% oxygen in CO2. And there are problems for you to work together to see how he did some of these things. So that's one of them, I believe. And then in 1801, carbonic acid, as it was called, was analyzed and found to be 28 grams of carbon to 72 grams of oxygen. Okay? Or in the case of nitrogen, there were several oxides that had these ratios, all as analyzed in 1810. Right? Now, you can look at the weight ratios if you want to. Oxygen to carbon ratio in the first one is 1.27, the other is 2.57. Or you can look in the oxides of nitrogen, and they're 0.58, 1.27, 2.39. Right? Now, what do you notice about these? Do you learn anything from this? I mean, these guys got these results and sat down and scratched their heads. What did they come up with? Anything profound? Any relationships among these numbers that you can see? Or are they just sort of random numbers? Yeah, Nick?
The ratios are kind of like
Can you speak up a little bit?
like the 1.27 is half of.
1.27 is very close to half of 2.57. It's not exact, but there's going to be experimental error, right? It's about 1 to 2. It's actually 2.02. And if you look in the case of nitrogen, it's 1 to 2 to 4, right? It's actually 2.19 and 4.12. So as always, when people develop things experimentally and observe regularities, there's a question of what's real and what's just experimental error, and you have no way of knowing at the beginning. We have a way of knowing now because we know what the true weights are. So they're integral values consistent with simple atomic ratios. So now we know what the percent errors were in these things. Okay, that the ratio of the error was about 5% or 4% off from what it should have been, and then oxygen, nitrogen, one is minus 2%, others are plus 11%. So within roughly 5% or so, they were doing a pretty good job of the analysis, but they were able to see through to this law of multiple proportions, and that's what you would expect if these things were made up of identical molecules with simple ratios of numbers of atoms in them. So this tended to support Dalton's ideas of atoms. Okay, so we've looked at Lavoisier, and now we're on further into elemental analysis, doing accurate elemental analysis, and the idea of atoms and dualism, and we'll see what that is right away. And to do that, we're going to focus on Berzelius, but also talk about Gay-Lussac. Okay, so there's Faraday, whom we've talked about already, Berzelius and Gay-Lussac, and also Davy in England. Okay, so here's Berzelius in Sweden, born in 1779. As you notice on the previous slide, all those guys were born within a year, 1778, 1779. Another guy that was born at the same time didn't make it to the list, but his statue is right below, who's Benjamin Silliman. He was exactly the same time. Okay, so here's Berzelius, who lived to be almost 70 years old and did an awful lot of stuff. So he was very good at analysis, both of organic substances and of minerals. In a period of 6 years, he accurately analyzed 2,000 compounds for their elements. Okay? He developed really good atomic weights. Remember, we just saw that these previous ones were off by as much as 10 or 11%. But he got very good ones for 50 different elements. Okay? He studied electrolysis, which we will see, and used that to develop the theory of dualism and how understanding reactions as double decompositions, and we'll shortly see what that is. And he did a lot of teaching and writing. He was the most respected chemist worldwide. He chose in his picture, remember when these people got their pictures painted, they always chose some emblem to put in. And he chose his textbook that he wrote in 1803, but he was a very important editor and summarizer of the year's progress in chemistry every year. And he developed the notation that we still use for composition. So you'll see that. Okay, notation for composition. We're going to look at its evolution from alchemy through Dalton to Berzelius, which is what we use almost exactly. Okay, so in 1774, this is a table printed in Sweden of symbols for elements and compounds. And you see, for example, here's vitriolum cupri, or vitriolum ceruleum. You know what about cupri? That's the symbol there of copper, right? So why would they call it, why would it have been called ceruleum? Can you see any word that's related to that?
Cerulean.
What's cerulean about it? I got some here. That's not it. That's not it. This is it. It's cerulean, right? Like the sky. Okay. Or iron, there's the alchemical symbol of iron. Or, and vitriol means sulfate, right? Or mercury sulfate, okay? Lead, okay? So these are the chemical symbols. Notice particularly nitrium at the top that comes from nitrates, okay? And we'll focus on that and see that that's exactly the same symbol that Dalton used for nitrogen. So he derived his symbols for atoms from the alchemical symbols, at least many of them. Not all of them. Here are some others, and here are the symbols that Berzelius used for the same elements, which you see are the ones we use now. Okay? So notice, so there were alchemical symbols at the beginning for Dalton and as you went across. But in the next row, once you get to iron, which is Fe in Berzelius, can you see what it is? It's a little hard to read at this resolution. It's a little circle with a letter inside. What's the letter for iron? Can you see it? It's in the middle of the second row. It's an I. Sorry, it's not such good resolution. And the next one is Z, and then C, and then L. Why? Z, zinc, C, copper, L, lead, and so on. Okay, now down below that are binary symbols. So you put two elements together, like H with O, H with N with O, H with C, O with C. Now, here's Dalton's logic about these symbols. He said, he says, when only one combination of two bodies can be obtained, it must be presumed to be a binary one. That is, if you get only one compound, it must be one atom of one and one atom of the other. Right? So what would water be? HO, or his circle with a dot and a circle. Right? Unless some other cause appear to the contrary that would show you that that's not what you should assume. Okay, the next row, the ternary ones. N2O, NO2, CO2, CH2. And what he said about that is when two combinations are observed of the same elements, then they must be presumed to be a binary and a ternary. So you have NO and NO2. What if there are three combinations of the same elements that give compounds? You see what he's going to observe? What he's going to suppose? Okay. Right. When three, a binary, and the other two, ternary. Okay? Okay, and how about if there are four? When four, one binary, two ternary, and one quaternary. Okay? So he's laying down rules of logic for the way atoms must behave. And it turns out, as we know, atoms have different ideas from Dalton's logic. There's nothing illogical about Dalton, it's just wrong. Okay, and this is Berzelius's notation for the same symbols that Dalton gave on the left, but you notice they're completely recognizable to them except for one thing. What's different? Here was ours, and here is Berzelius's. The only difference is he used superscripts instead of subscripts. Okay? And he decided to base the names on Latin, so it would be international, whereas Dalton had used English. And the formulas, notice, are not structural. You might, Berzelius's aren't. They're just written in a line and a number. These could have been assumed to be structural, that you thought the atoms were arranged that way. I don't know that Dalton really had that idea, but they sort of convey that idea. But Berzelius's don't. They're just a list of the elements and the ratio by weight of atoms in them. And he developed some more fancy abbreviations as well, where, for example, these little dots above elements would show how much oxygen was associated with it. So that chromat potassique was K with an O and chromium with 3 O's. Or down here he has some even fancier things. Notice the superscripts denote the number of atoms. And that this benzoic acid should be H10C14O3. Now wait a second, a carboxylic acid has how many oxygens? Carboxylate group? 2. Here he's got 3. The reason is that he thought there was water in these acids, so he heated the heck of them to drive the water out, and what you actually were left with was the anhydride. So 2 acids had come together and lost water, right? So the formula should be C10C14O3. He's got H12C15, so not so far off. And he's got these neat symbols for acetic, tartaric, citric, and so on acid, but those didn't catch on either. But his symbols for the elements did. Now, let's see what we got here. One more topic. Atomic weights and equivalents. Okay, these are Dalton's atomic weights that he used in 1808. Hydrogen 1, carbon 5, nitrogen 5, oxygen 7, and so on. Now, as of 2004, this is what they should have been. What's wrong with Dalton? Why is he so off so far, for example, in oxygen, which should be 16, and he has 7? How can he be off that much? Charlie? Can't hear.
Diatomic.
Yeah, what did he think water was? HO. We know it's H2O. So the ratio is off by a factor of 2, right? So all these are off, most of these are off by a factor of 2 or 3, depending on what the true formula we now know to be. Okay? But if you make that correction, this is what kind of errors he had in his atomic weights. They were roughly 10% or so errors, right? And the question in silicon chloride, Thomas Thomson in Scotland thought it was SiCl. Gmelin in Germany thought it was SiCl2. Berzelius thought it was SiCl3. And Odling in England thought it was SiCl4, so you could have anything you wanted, right? So which one is it? How can you tell which one it is? That's the problem. Okay, so this is when Gay-Lussac in France gets into the act. So in 1804, he and the physicist Biot made a balloon ascent to a height of 7,000 meters. That's way the heck up there. And in fact, that was a record for the 50 years. And they have a big flask they're carrying. Why? What do they want to do with their big flask?
Collect air.
Collect air at 7,000 meters and see if it's different. Okay? Okay, so they established that the atmospheric composition is invariant with altitude, at least at the heights they could do. But that's not the most important thing he did for our purpose. One of the really important things he did was figure out how to oxidize sugar, how to burn sugar cleanly. Remember, Lavoisier had to resort to fermentation. But he found if the source of the oxidation was sodium chlorate, then you could heat them together and actually get it right and get water and CO2 out of sugar. So that was a very important practical contribution. For the present purposes, he found that when you decompose water, you get 1 to 1 volume of oxygen, you get 1.9989 volumes of hydrogen. And if you do the same thing with ammonia, for a volume of nitrogen, you get 3.08163 volumes of hydrogen in his experiment. What did he conclude? What was Gay-Lussac's conclusion from this?
H2.
What do you think he thought the values would have been if there was no experimental error? How much hydrogen would he have gotten? 2. And how much hydrogen would he have gotten from nitrogen? 3, right? They're very, very close. Just a few percent off, right? And even closer in the case of water. So what did he think? He thought that the volume of a gas was proportional to the number of atoms in it. Right? Whose name do you associate that with? Avogadro, but both of them did it independently. And Gay-Lussac is the one whose data I'm showing here. Okay, so this was an alternative to Dalton's law of greatest simplicity. Dalton said if there's only one compound, it must be 1 to 1. Gay-Lussac said look at the gas ratios, and that turned out to be correct. Although it didn't get completely adopted for another 60 years. That's really funny. Okay, that's enough for now.